Okay, so probably I can save some time for the introduction part. Instead, I add some more details on the proof. No, this is some fancy picture show you in the gas dynamic. You might have a lot of shock waves. So because we talk about different type of shocks, so this is the invasive shock, and if you have a supersonic flight, you will see that. And if it happens a lot of, I mean, shock happening all together. So how to describe this shock? One way is to using the compressible Euler equation. But simply, if you only talk about compressible Euler equation, you're not going to have uniqueness because you have some easy unphysical solution without satisfying the entropy condition. So you want to add the entropy condition, and you want to select the unique solution, especially in 1D. There's a successful story. I mean, and in by the first establishing the L2 stability. This result we will review the earlier uniqueness result, especially by Alberto, and in the next page. But so I summarize 3 of my major results as a result 1, 2, 3, and we will focus on number 3. But give a quick introduction for result 1 and 2. And this was already introduced this morning by Alexis. And go back to the history of the uniqueness and stability result, especially for BV solution, satisfy the entropy condition. So the breakthrough happens in 1990s by Alberto, and this at least 4 together, but this should be Bresson, Goten, Bresson, Lovelock 1, Bresson, Lovelock 2, and Bresson, Lavishka. They can prove the solution is unique. Some conditions are satisfied. 2 of them, either the boundary variation condition, which means the solution is has a bounded total variation on each time-like curve, not only on each time, and the time oscillation condition. That one is a little bit harder to explain. And then big, progress and in 1990s is on L1 stability, and they can prove the solution. BV solution is stable in the L1, and for the general Cauchy problem, small data because we only have existence in the small data. And the L2 theory happens much later. In fact, the basic tools called the relative entropy method was known much earlier in 1970s. We will briefly introduce that later. And but in order to jump from small solution to and one single shock to the Cauchy problem is much later. I only write on the result. We did finally solving this uniqueness as L2 stability, but I will review the earlier results later. And this now works for 2x2 system and the 4 Euler equation. So and recently, this is a joint work with Cooper, Phil, and Sam Krupa. We can show the L2 stability is in fact the holder, and one page you will see holder is the best you can expect. Okay, you're not going to be able to get the Lipschitz stability in L1 because the nature doesn't give you that. And also, yes, we do have some, in fact, some kind of contraction, so it's much bigger, much stronger than simply the stability in L2 sense. Then come back to the this one solve the uniqueness because we can show the boundary variation condition is always satisfied if you have a BV solution. So combining with the Bresson-Lavishka, we can claim uniqueness without that condition. And this then is becoming really nice. Progress in the uniqueness part, especially in 1D. Now we have pretty complete understanding for the small BV solution, especially for see the paper of Bresson Delalis and also another one with Guerra. They show the BV solution for the general system conservation law, in fact, satisfy the time oscillation condition. So unique. Now we don't have the issue list in the 1990s framework, the a priori assumption. And there are a lot of some recent progress, especially for this large BV solution, especially in the Gleim-Lux regime. People can show some really nice progress on the uniqueness result. Especially there's 2 papers, and there might be more. Okay, as Alex said, you need to keep very close tracking of these young guys in order to make sure you get the latest information. Okay, very nice. Let's go a little bit general. We also have several other type of shock waves. One is the dissipative shock, and especially we also want to know its emission limit. This is a fundamental open question because this tells you why the Euler equation is validated in physics. Because when you derive Euler equation, you just omit the viscosity. For gas dynamics, this is a good kind of assumption, physical relevant. But remember, in the real world, you always have slight viscosity. So in the process of inviscid limit, you should be able to take limit from Navier-Stokes to Euler. If you consider smooth solution, that's pretty easy. But if you consider BV solution, especially you might have infinite many shocks, this is highly non-trivial. So definitely don't want to say too much because this was just done hours ago by Alexis for this result, our result, and also two other major earlier results. And let's focus on this. Okay. The third type of shock waves, I would like to call it shock wave because you also have the feature of the shock wave on two sides. You have difference, but this time you do see the oscillation, and this is coming from nature. Think about if you have experimentally, if you have water tank, and on two sides the water level are different, then the water will move from high to low. But they do not just all of a sudden moving this way; they will oscillating and then drop. Okay. And this is can be described. One of the fundamental model we can use to describe this phenomena, okay, is this KdV Burgers equation. We will talk about that in detail. And this is a very recent result. We posted in the end of the February and probably 2 months ago with my two collaborators in Korea, Mongjin In and Mongjin Kang and Namyang In, and also Yanan Shen. And we proved the L2 contraction. Contraction definitely under some shift because otherwise you're not going to be able to have any contraction. We will see the definition, precise definition soon. And also this L2 contraction automatically give you the stability of this kind of dissipative shock, especially with infinite oscillation. So if you have oscillation, you will have infinite oscillation for the KdV Burgers equation. And also we can take the zero dispersion dissipation limit. Okay, you will see why we call dispersion dissipation limit, because we need this dispersion dissipation coefficient to go to zero together. Okay, under some range. Okay, so sure.
What do you mean by infinite oscillation? Like if you fix dispersion and diffusion,
yeah,
will that single shock or the single thing you have there oscillate infinitely many times?
Always. We will explain very quickly. Always infinite oscillation. Okay, so relative entropy. So Alex didn't show this. So this is the relative entropy metric, and is using this metric. This is more or less a Taylor expansion, and eta is the convex entropy. And because it's a Taylor expansion, so the error term is related to the square, and also because the eta is convex, so the Hessian has sign. So this metric is exactly equivalent to this R2 norm. So the result is if you have a smooth solution, and this is for the Euler, which this is for the hyperbolic conservation law without viscosity and dispersion, and this UM is a bounded weak solution. Then if UM is going to U0 in L2, then UM will go to U in L2 for the later time. Although if you have U in smooth solution, you can have a much stronger result. You can show the Holder stability. But this is the starting point of the story. And then this result was started later by especially the paper of Guiqiang Chen, Harmonic Fried, and Yachun Li. They can show the human problem. But jumping to the thing, including shock, things are more complicated. This is exactly the picture Alex is using today. Good. Just show that if initially you have O epsilon perturbation in L2, later you cannot guarantee O epsilon. In fact, you only have O square root epsilon due to the norm. There's remember there's a square root inside the L2 norm. And the idea, there are many ideas for Burgers equation to show such kind of Holder stability. One idea is that you just instead of compare the shifted shock and you compare with the shifted and psi, then these two guys, you don't have this square root epsilon. And where the square root epsilon order error hidden is hidden inside the shifted shock and the real shock. But remember, no matter shifted shock or real shock has really simple structure. Both of them are just has one jump, a constant on both sides. So calculate their error is super easy. It's square root epsilon order. Okay, so this is only one way to show this Holder stability for one shock burger. But the good news is this one gave a building block for us to extend it to finally 1D 1D hyperbolic conservation law with the general BV data. I should say the major breakthrough to make it into the Cauchy problem is this paper by Golding, Kripa, and Vasu. Maybe your PhD thesis, right? I guess. Yeah, and one of the papers. So in this one, we have the important building block to talk about the weighted relative entropy, especially the weight is very precisely calculated, so we can send it to the Cauchy problem. For Cauchy problem, you can not only think about one shock, you have infinite many shocks could be. So we need to modify the from tracking scheme. Modification mainly adding shift, and also the hardest part is to define the weight very precisely to make it well defined after wave interactions, especially. This is my joint work with Krupa and Vasu. This is also my first paper in this direction, which is very exciting. We done that right before the COVID, and but finally published several years later. And there are two papers. In fact, another one we showed the L2 stability for full Euler equation with the non-isentropic case. Okay, and this is a recent result. And as Alex said this morning, now we can do the quantitative stability, which means especially show the rate is exactly Holder in the square root epsilon order from epsilon to square root epsilon. That's the best we can expect. And we really think, I really think at least this one can be used to generalize a lot of results. Seems like we already have some progress from Vasu and Jiayun, right? So the key idea, I didn't write it out, but it's we find additional decay or dissipation for the shock field. Okay, so in the quadratic order. So, let me focus on the dispersive shock. So I just quickly list the results. The second pass. Now I summarize this L2 theory into 3 paths now, very proudly, because the third pass we finally get it for dispersive shock. So the first pass is for the emitted, consider the emitted fluid and directly solve the stability and the uniqueness, whatever. And then we can do the viscous path. For the viscous path in 1D, the viscous path, we even can take the emitted limit, but also we can do the viscous path for multi-D solution. Think about the multi-D solution is exactly Navier-Stokes. So the L2 theory for this stability for the viscous shock for Navier-Stokes in multi-space dimension is also a very interesting problem itself. And this is by Deformus and from smooth to Euler, and this is a very nice paper. And Kang, Vasu, and Iwang, they can do the Euler contact discontinuity, which means they can do Navier-Stokes and then take a limit to the contact discontinuity for Euler. And if you have the shock wave, currently we cannot do the multi-D case, multi-D stability. And it's still in the Navier-Stokes level, but this is something we are working on right now. This is the result for the emission limit. If you want to take a look, so 2 parts. The first part is the existing part. If you have 1D Navier-Stokes with small BV initial data, that one will convert to the unique BV solution for Euler, and as viscosity coefficient goes to 0. And also, since we already showed the BV solution for Euler is unique, so combined together, we can get this existence result, and the existence, the limit is a unique solution. And the second part is more or less the stability of the emission limit process. So this U is a small BV solution, and U epsilon we perturb after we perturb the initial data, put this one instead of to Euler, we put this one in Navier-Stokes, and let the Navier-Stokes solution taking limit and to give you a solution in Euler, and the Chen parabolisa can guarantee the limit always exists. And then after we taking limit, we compare the U epsilon and U both solution for Euler, we can get it's still not far from U, but this is in R2, this is in R1 log. So this is the result we have. Currently, this I didn't write it down, but this is in fact for isentropic Euler, and with in Kang and Vasu, we are also working on the isothermal case. There is a chance we can do it for Euler, but that one is pretty far still. Okay, so any question here? Very quick, but just a summarize of the results, and if not, then let's go to the main part of today's talk for the KdV Burgers equation. I think I do have time to show some proof, if you don't mind. Let's because the equation is quite its first fundamental, second one is quite simple looking, at least not just one full page of systems. It's only one equation, and this epsilon I need to ask you to remember this epsilon is the coefficient for viscosity and delta is the coefficient for dispersion. And we can, one of the feature for this equation is you can use this equation to describe the dispersive shock, and especially this epsilon is important to describe the dispersive shock, which means on two far fields of U tilde, the traveling wave, you have different level of the water. If your epsilon equals 0, you at least you can't do it, can't describe it simply just by traveling wave. We will see why this is true. So for the traveling wave, just plug in, you get this equation, and also this is our important initial data. So say at Kc goes to negative infinity, water level is high, and the other water level is low. So you can think about U as the profile of the water on the top. Then multiply U tilde prime on both sides. Also, you need to remember U tilde is the traveling wave, and U is the solution for the equation. Then you get this energy is dissipate. So because remember our parameter is our parameter Kc has this kind of we started the stability of the equilibrium when Kc goes to negative infinity. So if you write down d negative Kc, this will show the dissipation of the energy. Okay, this V is the effective potential energy. So this is the potential energy and the kinetic energy. Okay, we will come back to use this equation later. Maybe we can write down somewhere. Okay. E equal to VU tilde plus delta over 2 U tilde prime square, and V is the polynomial. Okay. So let's talk about the equilibrium. Okay, you can linearize the equation. If you linearize the equation, you can simply, if you linearize this equation, you will simply get a spring mass system, nothing else. And for that spring mass system, okay, if you I can write it down, linearize around U tilde equal to negative S. Okay, because the picture is this. U tilde equal S. This is the S, this is negative S. Okay. And if you linearize around S, you will simply get delta U tilde minus epsilon U tilde prime plus S equal 0. I believe it's S, okay, or 2S. Anyway, yeah, S. Okay, so for that system, for that, where's my U tilde? For that system, let's write down another one. So that's because the small v equal to U tilde minus S should be V. Okay, because we linearize around the U tilde equal to S. This is capital V. This is small v, and this then you in order to study the property of the this linearized the problem, you just need to talk about the eigenvalue. The eigenvalue larger or equal to 0, we know this supreme mass system is overdamped. So you have real eigenvalue. So the traveling wave is monotonically increasing. So you have this picture. That makes sense? Right? Because in that case, it's not oscillating. Your solution for that linear system is, say, e to the negative something, okay? E to the negative Cassi something. But if you have a negative eigenvalue, then you have a complex, you have this one negative, then you have a complex eigenvalue. At that time, you have a oscillative case. So the solution behaves like a cosine sign, okay? And the decay of the energy E also tell you that you will have the oscillation becoming smaller and smaller because it goes to negative infinity. We will precisely calculate that. So this blue dot picture is corresponding to when E is a constant, and when E p equals 0, so corresponding at that time dE dt is a constant. And when E p is larger than 0, when there's a dissipation, then your trajectory is breaking all the E equal to constant, and finally give you a unstable spiral. Okay. We are interested in that case, but I will start to show the idea by the monotonic case to how to show the stability. So first one, what's the meaning for the contraction is we want to show this time derivative of the L2 distance is less than 0. And here you see the negative x. The negative x is exactly corresponding to the shift. And for the Burger equation, we already see the shift is necessary. Otherwise, we're not going to have contraction because it's epsilon to square root epsilon. So we compare the solution with not the exactly traveling wave, but it's the traveling wave adding a shift because the perturbation will put the position of the shock slightly different from what it was. And we have 3 terms. And these 3 terms, I don't think it's necessary for me to talk about how to calculate that, but I want to leave it because I know this slide will be available for you guys if you want to take a look. I just want to show the calculation not hard, pretty easy. And I don't know who gave this first. That's always I'm embarrassed. And but this was there for pretty long. Okay, someone told me it was known much earlier. I don't know. Maybe Kevin knows that. Okay, but at least I don't know. Yeah. But anyway, this expression, this y is, you see, the average and of the difference, and then this b is more or less the L2, and this g is the L2 of the derivative. So these 3 terms looks exactly like a good pair of the Poincare inequality. In fact, you need to be careful. This is maybe the notation might be the invention of Monique Kang and Alex Vassou. They use b for bad term. Because remember the profile of U tilde is decreasing, so this term is negative, so negative plus. So this is the bad term, positive term. And this is a good term because I hide the negative sign here. I call that G. They call that G because it's a good term. Okay, so let's do a slight change of coordinates and move this negative x to U. Then we have this equation. This is what we got from last step. And this is the summary. The idea is for monotonic case, for example, or even you just simply just let the delta equal 0 without viscosity for dissipative Burger. The same thing. You use the shift x dot equal to negative ky. So to create this average square, then this it looks very similar to some kind of Poincare inequality. So I need to mention the earlier result of Barker and Broxy, Her and Yang, and they give a sufficient condition for the L2 contraction, but without using this kind of the Poincare inequality idea. And they can verify the condition for the monotonic case. And for non-monotonic case, the sufficient condition for L2 contraction, they can't verify analytically. They give some numeric evidence to show is good when the eigenvalue is less than 4, something like that. So what we do is we give a rigorous proof for this one, less than 0, for a non-monotonic case, but not all the monotonic case. For some case, when the threshold and S delta over epsilon square is larger than the threshold 1/4, but less than some number. Okay, and also this also provide a new proof for the monotonic case. I think it's a pretty easy proof for the monotonic case. Let's go starting from the monotonic case to show you some idea. So remember, this is the thing we have. Okay, now we do a transformation. We are allowed to do this transformation for a monotone case. For monotone case, that means your tilde on the Cassini plane look like this. This is S, this is negative S. So at that time, you can change. This is allowed. This is allowed because U tilde Cassini is always negative. So change of coordinates is okay. And this Z just more or less means U tilde, just exactly U tilde, because du tilde equals U tilde Cassini d Cassini. And then changing the coordinates, to go back a bit to this one, then you see this two can combine together is dz, and this one combined dz, and this part is a little bit tricky because you need to change both z Cassini to z here and Cassini to z over there. I can write it out. Okay, easy. So it's W Cassini square d Cassini epsilon, which is equal to, if you write down into z, you should have dz d Cassini square, and dz here is the d Cassini dz. Okay, you see there cancel one. Okay, so that's what we have. And remember, z is nothing else, is just U tilde. So dz d Cassini is U tilde Cassini. I write negative sign there because now make it to be positive, and then there's negative sign here. There should be a positive sign. Okay, I'm sorry, because there's negative sign. Yes, this is a good term. Yes. So this is what we have. So the idea is using this Poincare inequality to show the right-hand side three terms, the summing up is negative. So the first one is exactly the first one. Choose S to be B, negative S to be A. And the last one is exactly that one. And the middle one is not the same. So in order to show that, essentially you only show this inequality. Make sense? Okay. And this Poincare inequality was used to do the stability for viscous shock. In fact, for viscous shock case, this U Cassini and this S minus U tilde plus S with some coefficient are exactly equal to each other. Okay, so that's one of the motivation why they use this Poincare inequality. And this Poincare inequality can be proved. They prove that using the Legendre polynomial, so which means they change it to a Sturm-Liouville problem. The Sturm-Liouville problem has the weight is equal to 0 at any point. Okay, so this is not the trivial Sturm-Liouville problem. Is the kind of the bad case, but not the worst case. Okay, it's still doable. Okay, so how to do that? I think I have time to run the proof. Okay, to show this inequality in red. So how about I just call the U Cassini to be HA and PA to be alpha A minus S A plus S. I need alpha to be larger than 1 over 4. And this is the heteroclinic orbit. And for this heteroclinic orbit, monotonic case is just one line. And more or less, I need to compare this guy because this is on the U tilde U Cassini plan. And U tilde prime plan. U tilde prime means the derivative on Cassini. And on this plan, you compare this heteroclinic orbit. At that time, it's still not a heteroclinic orbit because it's a monotone case. And with this polynomial, with this parabola, and comparing with that, in order to show that, we just recall the equation for the traveling wave. And this equation, if you divide U Cassini on both sides, then the U Cassini divided by U Cassini by a simple L'Orbital rho, you can change it to the du Cassini du. And this was known long ago. You can get it back from, for example, Jerabona and Schoenbeck. And it translates this language into the H. And remember, H is U Cassini, then that means H prime. That prime is taking derivative on U. Okay, and right hand side you have this. Okay, then what we want to show, we want to show HA is below PA. So H is the black and the P is the red. So the black curve is below the red curve. Red curve is quite simple, it's just a parabola. You first need to check the endpoints. It's very easy to say HA and PA are the same at A equal to S and negative S. but you need to check the derivative. And that part is not hard. I will leave it to you. And for example, at the left endpoint, you need to check h prime negative s less or equal than p prime negative s. So make sure this h is lying below p. And then we can prove by contradiction, this red wave is always above the black wave. Assume they meet each other at some point larger than negative s but less than s. Then if these two guys meet, I should have a picture, but I didn't prepare for that. So if this is the wave, we want to prove this picture is correct. But unfortunately, if not, then they hit at B at Kc equal. This is the U tilde and U tilde Kc plan on the phase. This is the phase portrait, and at that time, you calculate h prime b again. And remember, at that time, HA and BA are the same because the two curves meet. So you change. And this PB almost completely cancel the numerator because the PB take the same expression almost at the top. So you get this one. And if you plug in this square root 2 minus 1, you will see the left-hand side exactly less than right-hand side. Okay, the easy calculation. You might ask why this number coming from. In fact, this number coming from when you check the 3.1 at the left endpoint. Okay, at the left endpoint is the crucial one. And left endpoint corresponding to U tilde equal to negative s. And this is U tilde equal to s. Okay, U tilde equal to negative s and s. Okay. So this tells for monotone case, you can apply this Poincare inequality to show this time derivative of w squared is negative. The hard part is the non-monotone case, of course, because monotone case has already been done before. Going to the non-monotone case, when you break this critical points to make it into the oscillatory case, so you do have the picture like that. At that time, you have a heteroclinic orbit, and because the curve will break the E equal to constant for all the E equal to constant. And then this is U tilde equal to negative s, U tilde equal to s. If you compare the picture, you will see U tilde to negative s is a non-oscillating point. All of a sudden, you will starting from this point, we call that U0 drawn to negative s, which corresponding to from here, this is U0, all of a sudden to here, because this is a U plan, this is a U tilde plan. And also, this is the U tilde, U prime equals 0, or partial Kc equal to 0, because if it's below U prime equals 0, that's corresponding to the decreasing, then increasing, right? Then decreasing, then increasing. So that's the phenomena, and for the traveling wave. Okay. So you see the trouble for the previous step, if you still remember. The crucial step, we use this dz equal to U tilde Kc d Kc for the transformation. This is okay if your U is monotone. If U is not monotone, you can't do the transformation globally. Okay, we do the transformation on each cycle. Okay, you have options, right? We do the transformation on each cycle. So on each monotone interval, we can do the transformation, but we can't do it globally. Okay. So if you do that, fine. Then you see this now. If you do that, then this term is the same as before. This term is almost the same as before, but you get trouble here because this average square is useless. Because this average square is on R, not on each interval. If you do the transformation from Kc to U, du tilde or dz, then you still want to use the Poincare inequality. Then you need to use the Poincare inequality in each monotonic interval. If you want to do that, you need the average square, but you don't have it. Because average square was given. This is still useful, this term, but this is you cannot directly use it clearly. That's the main problem. And also remember, if you do this transformation, you need to do the transformation in infinite many intervals. It oscillates infinite many times. Okay. The first key idea is to create. We want to create the average square. We're not going to do that in one step because this is the hardest part. So think about this gi from u this point to that point, and on the same level of u, this is the dispersive shock. This is on the Cassie u tilde plane. Okay, if you have that, then we want this average square. We can do the integration by part, because we first write down u tilde minus ui. Ui is just constant, some constant. Okay. Oh yeah, sorry about that. Some constant corresponding to u level. And we can do integration by part without cost giving any boundary term, because we assume these two guys have the same u level. So u tilde minus ui disappear at the boundary. So we can do that. After doing that, then we can use a very easy Holder inequality to get this term and that term. And you see, what's this? This is a diffusion. And this diffusion we have. And also we have extra, in fact, especially in the last the monotonic piece. Okay, I will go back to show you. And then, and also there's a cost here, the L2 norm. So why I say that we have more than we need, because the alpha here is the square root of 2 minus 1, more or less 0.4. But in the Poincare inequality, we only need 1/4. So we do have room. That room is crucial. Okay, so which means we have some kind of extra diffusion, call this diffusion term in the last monotonic piece, in that piece, more or less. Especially in this case, we have some extra. But this is still not enough. The reason is what we want is for example here, what we want is this average square on the monotonic decreasing piece. But what we have is on a piece from here to here. We still need to get that simply the average square on the decreasing part. Okay, that's the hardest part. But first, even before that, if you want to apply this inequality, you see you cause some dissipation, right? And you have infinitely many times. What do you worry? We worry, can we have enough diffusion to make this process happen in infinitely many steps? So we need to calculate the infinite sum of that. And not only show the infinite sum of that is finite, we need to know how big this infinite sum is. That's one of the hardest part. So which means like, if you do the linearizer problem, you know, this is the BV. That's definitely not enough. We not only need to know this guy is BV, we need to know this guy, how big the BV norm is. Okay, so that's the hardest part. Another. And also, in fact, to calculate this L2 is a pretty hard job. Okay, so we need a precise estimate on each extreme, the distance from the extreme to the equilibrium S. Okay, so we need to know that, and also we need to know the decay rate. Okay, how could we do that? Okay, first show the results. Okay, oh no, sorry, go backward. This is what we have. There might be some room to improve that, but I should say at least in the first cycle, we get pretty nice estimate. You can say this U0 minus S. If A equal to 1/4, that's a critical case. Without oscillation, this U0 minus S over S should be 0. At that time, our estimate can give you 0.01. And when 1/3, and this more or less is quite close. I remember this one should be 0.11. I mean, if you run numerics, but this is, you see, it's quite close. So as I explained, we need a nice expression for the each equilibrium, the distance from that each the extreme value and to the equilibrium. And so this is our result. The rho star and the rho up star, rho star is the decay rate. So when A equal to 1/3, you see, so which means this height is the decay from right to left each time by 1/6. So if this distance is 6, then next one gonna be just 1. Then next time is 1/6. So decay really fast. Okay, and in fact, our calculation just the numerics just shows if even you go to the case when A equal to 10, the decay rate is still pretty fast. Okay. Okay, if you really want to know the expression we got this explicit formula, but maybe kind of useless. Okay, how we got this precise estimate for the local maximum and local minimum? That idea is really nice and pretty easy. In fact, this E, after we found it, this E is the energy. Not only we know that, also we know dE dkc equal to epsilon u tilde prime square. Okay. Here in the calculation, I just make life easier, set epsilon to be 1. Okay. I didn't write it down. Sorry. I just said, I keep the epsilon. Sorry, the epsilon is there. Good. So this one is that guy. And what does E infinity minus E kc0 equal to? At these 2 points, remember, the kc0 is corresponding to the rightmost, the extreme value. So at both this point and the far field, we get the derivative of u tilde is 0, which means we don't have kinetic energy. Potential energy, remember, is just some third order polynomial. So we can write this one as an equality, not inequality. The only step we use inequality is from here to here. And that means we want a very precise or very nice estimate of u tilde prime and f. F should be some algebraic function, because if we make f to be algebraic function, we can make this last step integrable. We can write out the integration explicitly. And here you see we leave one of u tilde prime, and this u tilde prime negative, you can see exactly give you du tilde. Remember, we consider this inside each monotonic cycle, so we can make this happen. And then left-hand side, right-hand side are satisfy inequality, and this inequality give you a bond, really good bond for u0 minus s. If you can get this only inequality step, a good estimate. Okay, so here is the f we use. Okay, here is the f we use. So essentially, it just means you need to compare the f you use and the heteroclinic orbit. Remember before, for the reason of Poincare inequality, we compare the parabola and this curve, but parabola definitely not a good fit for the picture. For example, for the rightmost cycle, you see the left-hand side is look like a parabola, but the right-hand side is more looks like ellipse. The derivative equal to infinity. So finally, after a lot of tests, we choose this. So we believe this is maybe the first 2 term of the expression. You can do more to make it more precise. And after getting this expression with the optimal lambda and mu, we can get, this is a real picture. This is a real picture, and what the right-hand side look like, and what the heteroclinic orbit using numerics. You see the fit really nicely. So that's the reason why we get this time the error is super close to the real, and real means that from numerics. Okay, we can do better. Okay, if you explain more terms. And the first one is for the purpose of the Poincare inequality. For inside circle, it's more or less looks more like ellipse for each cycle. So we use the square root. Okay, and we can show the coefficient is in fact decay exponentially, and it's in fact a to the i's power. And this I is pretty small, 1/6, 1/4, as we showed before. Okay, combining this information, now we know what UI are. Okay, very precisely. We can apply this inequality by summing up these red terms, still get a good control on that, but that's not enough. As we said, we want, for example, in this piece, we call it GI plus 1. We want the square of average in this decreasing piece only, but not just coming back. This is really troublesome. And so we need the square of average. We need the square of average on each decreasing interval, but not means half of the GI or half of the GI plus 1, but not the full GI. So for that piece, we need this one. Okay. So the idea is to move the additional decay from the rightmost decreasing interval, because the coefficient we prove is more than we need for the Poincare inequality. Okay. I do have some time, so a little bit. So let me just give you why this is not enough. Okay. So in fact, we found this L2 norm and this average square, you can treat one by one in that sense. So first, this is a very simple Holder inequality. Take a W and the square root U prime, and take another square root U prime, do the Holder inequality, then you get that. So this is the variation of U, okay? And we can also do backward. How to control the L2 norm by the average square? You can use the Conva-Su-Poincare inequality. But remember, this step is not free. If you use this step, you cause some diffusion inside this kind of Poincare inequality. So more or less, this can treat, okay? And the good thing for this one, you need to remember, because this one is summable. You can divide into sub-intervals. But this one you can't. Left-hand side you can't, because that one is average square. So the trouble is, if we want to use the thing on Ji plus 1, which is on this the whole piece, the average square, to get the average square only on the decreasing piece, we call that AD, D for decreasing, AI for increasing. But good news is, remember, in the increasing part, the L2 norm has good sign, not bad sign, because the L2 norm give you the bad sign when U tilde prime is negative, but this time U tilde prime positive. So the three terms, the YGB, are all negative sign. So we not only don't have to control, and we even can use it. So we can use this L2 norm to create some average square, and this average square and this AD plus AI is exactly the Ji. Okay, assume you have a good control of this L2 norm. You can, let's see, assume this AD plus AI square is infinitely large. But even it can be, right? It's very large. But even you have that very large, you see, this very easy Cauchy inequality, if you want to consider control 1 times AD square, you need at least 1 plus A AI square. Unfortunately, we don't have. Because this coefficient are exactly corresponding to varying in U. And in this piece and in that piece, exactly the variation of U are the same. So we cannot use one of this to give you one of this. We need, in order to give one, we need 1 plus A. So we need extra the average square on the increasing part. We can't do it. The idea is to run an induction using the actual decay. So in fact, we can use actual decay to get some L2 norm and then move to left-hand side, the average square move to left-hand side, change to L2 norm. The L2 norm you can break, then you can do the rest. And we can make this happen because we have exponential decay on the traveling wave. So the height is decay exponentially. Okay, so we can make this happen. And the hardest part is right now is to calculate how many diffusion cost you used. We use the diffusion cost a lot of time, and make sure the diffusion is less than the actual diffusion you have. That restricts the result to right-hand side to be some number, currently 1/2, but in fact we can do 1, but make the paper much longer. But definitely we have room to push this number much higher. I didn't say I can push this number to infinity. That's impossible. But pushing to somewhere like 3, 4, or even probably even larger is possible. Okay, and it's very possible. And this is the result for the decay. So more or less, you see this term is less or equal than initially. And this also gives you some control on the shift. This is the Lipschitz shift. And as t goes to infinity, the speed of shift goes to 0. And because our estimate is uniform, mainly depending on this parameter, so you can let your delta and epsilon, these two parameters, go to 0 together. The only restriction is you need to make sure this parameter is inside the domain. Okay, we can handle. So that solution will finally converge to the solution for implicit Burger equation, probably with shift. Okay, so that's what we can got. Okay, this is some physical relevant picture to show the problem is the physical relevant. In fact, now we can extend the result to the stability of the planary dispersive shock with oscillation for the 2D, for one of the 2D water wave model, for the called KP equation, I need to be careful because I add dissipation. So it's a dissipative KP equation. I believe it's exactly describing this picture. Okay, so this is not inside the experiment. You have a long water tank. Now it's in the river. You really have 2D with in the say y direction is in bounded domain. Okay, on a torus. Then you see the oscillation, the perturbation of the dispersive shock, planetary dispersive shock is stable in two-space dimension. A good question is, can you do more? Those are the pictures from the Chen River, and this is from somewhere in British. I forget the precise name, but can you do this picture? So numerically, there are very nice pictures by this Biondini, Bivolsik, and Mark Hofer, and they show this numerical pictures showing the macro reflection for the 2D dispersive shock for the KP equation. And for that equation, you see they initially starting from some kind of angulized the initial data. That's leftmost picture is the initial data. Then you get this kind of numerical result. You can, for example, say this one is just quite close to the picture we have over there. Very nice, especially this one. When two rivers are meeting each other in angle. So that might be some very interesting problem we can consider next, but definitely not easy, right? But just show you some possible track. Okay, thank you. I'll stop here.